Morning. Mhm.
Good morning to the people who are from USA and good evening for the Indian viewers.
Good
Uh,
evening.
I welcome all of you for the fourth
Great.
webinar, fourth webinar today. First, I'd like to thank all of you who are all instrumental in making this particular webinar happen in difficult times. I have a short explanation to make regarding these last three webinars, what we have done, a slight review. There were a lot of emails have come to us, to me also, uh, asking for a lot of responses. Unfortunately, we could not concentrate that right now because we are also trying our hard to manage the rest of the webinars, contacting presenters, everything. We will shortly look into that. Second is we stopped yesterday the training actually because we took we took this reason because of the interesting topics were there. But I think today we will have the training session. And regarding the question and answer session, uh, yesterday was a lot of questions were there. I could not allow it because we are already past the time. So this today I would request the speakers to uh, keep their time. We have given the timings to them around 20-25 minutes. You have to complete it. We will have discussion about 10 minutes. So everybody like to communicate and talk. This webinar is to create basically the interest in the engineers to come into the technology fold. So I think speakers can do within the time, if possible, would be very great. So we can cover all of them, question and answer, because that is going to be the important part. Question and answers, the youngsters will learn. At least we can take about 5 questions per speaker would have been good. Next is the feedback. I have received only 4 feedbacks. We are given a feedback. I think people send me personally a lot of questions afterwards in WhatsApp and everything. I would request them please to put on the feedback form. Click and enter in the feedback form. Till now, four responses we got only. In that we find people want to have live streaming, video streaming, and otherwise they are very happy. But I would like to remind those people this live streaming is difficult with this type of webinar, and especially with the bandwidth what we are getting in India to get a continuous bandwidth. So the idea is not a research paper we are presenting here. The idea is to make the interest first, the youngsters to learn technology, what is new available, and the managers today or the scientists to start really planning their research in a productive way. That is the objective. So we are doing it. And I would like now to hand over to Dr. Indramani to introduce the speaker.
Thank you, Syed. Uh, Professor Singh and friends, welcome to the fourth day of webinar. We have a very important speaker today, Manoj Karki. Manoj was born in eastern hills of Nepal, and he has, if you see his education, very varied. He did diploma in civil engineering, followed by BTech in computer engineering from Tribhuvan University, Nepal. Then he did masters from AIT, that was in remote sensing and GIS, followed by his PhD in agriculture engineering and human-computer interaction from Iowa State University. So you can see the range, as an engineer he covered. He leads a strong research program on sensing and machine vision and agricultural robotics in Washington State University, where he served as an associate professor. And that center he leads, and that center's name is Precision and Automated Agriculture. He has large number of publications in general of field robotics, computer and electronics in agricultural engineering, transaction of Asabe. And he is currently serving as elected chair for International Federation of Automation and Control. and associate editor of Journal of American Society of Agriculture, Transaction of American Society of Agriculture and Biological Engineers. He has been basically awarded, of late he has been awarded, and I would like to just mention that one. Dr. Karki basically, he is guest editor for Censors and editorial. He is in editorial committee and member of information processing in agriculture. Dr. Karki was recognized in 2019 as pioneer in artificial intelligence and IoT. It's a big recognition, and by Connected World magazine, and was featured as the Western Innovator by Capital Press. Friends, this is why I'm mentioning all this, that his connectivity and his expertise may be used by fellow engineers whenever his area of expertise, then kind of person we are getting for this webinar. So a warm welcome, Dr. Manoj Karke, and now floor is yours. Thank you.
Thank you, Dr. Mani and Dr. Ismail, for your introduction, and thank you everybody for giving me this opportunity to present and share some of the work we have been doing here at Washington State University. And depending upon how much time we'll have, I'll also try to introduce a few of my thoughts in terms of where we might be going in the future. Again, thank you everybody for being here. Let me try to share my screen and we'll go from there. Give me one quick second. I'm trying to do it here. Do you see my slides?
Yes, go ahead, please. Blank screen, yeah.
Yeah, so I'll start with these two pictures and give everybody a couple of seconds to kind of visualize them. So again, I'll be talking a little bit about artificial intelligence, cyber physical systems, and robotics as it applies to agriculture, in particular in specialty crop agriculture. When we say specialty crop, we at least defined by the United States Department of Agriculture, it includes fruit crops, vegetable crops, nuts, and some horticultural, some nursery crops such as flowers and things like that. And again, towards the end, I'll be talking a little bit about where we might be going in the future, depending upon again how much time we would have. But I'll try to keep it within 25, 30 minutes, and then we'll have time for questions and answers. First, I wanted to spend a minute or so talking about where we are located in the United States. Sometimes when I talk in international seminars like this, Washington, D.C. and Washington State have been misrecognized. So I just wanted to point out that we are in the Pacific Northwest region of Washington, United States. Washington is the state that's right next to the British Columbia of Canada. It's just above Oregon, as you can see, in the Pacific coast. Our Center for Precision and Automated Agricultural Systems, is located at the south central part of the state, which is strategically located there because all the specialty crops we work with are around us. We have many different commercially valuable crops, economically valuable crops for the state of Washington, including apples, cherries, wine grapes. And it also produces a lot of dry land, dryland wheat, as well as vegetable crops such as potatoes. So now talking about automation and mechanization, as many of you know, agricultural mechanization was recognized as one of the most important engineering achievements of 20th century. I think it was number 7 among 100 recognized. That's because over the last century, or a bit longer than that, we have developed a lot of mechanization solutions for farming that has revolutionized how we do farming. In the United States, for example, farming population went down from about 90% to less than 2% involved in farming. Still producing a lot of agricultural products which have been exported around the world, again, through this involvement of just 1% or so of US population. The machines like these, large tillage machines, large planters, boom sprayers for row crops like corn, soybean, wheat, harvesters like these, combined harvesters for corn and wheat and soybean, sugarcane harvesters like these, guidance and auto steering systems, such as the one we can see here, have been widely adopted around the world in recent decades. However, the benefit of all these mechanized or automated solutions have been to mostly annual row crops, such as corn and soybean. We still are lacking to utilize the benefit of these kinds of advancements in crops like apples, particularly what we call specialty crops. We started with these two pictures. As we can see, these two pictures were captured some 80 years apart, but in the basics, they are the same. We're using a ladder, there are manual pickers, using a bag goes on their front, and they climb up and down the ladders, pick apples, and bring a heavy load of apples up and down these ladders and empty on a container and repeat that process. For that matter, ever since we started or we knew how to build these little ladders, perhaps the way we harvest apples, for that matter, we harvest many different kinds of fruit crops and vegetable crops have not changed. And I think with all the advancement in artificial intelligence, parallel computing techniques such as graphical processing units, with advanced sensing data analytics techniques, and advanced robotic techniques, I believe we deserve better than how we are doing these kinds of operations in specialty crops. There has been long research and development in this area. Not to say that we just started a decade ago, or I started working in this area. There has been long efforts going on around the world. However, limited commercial success. There are a few aspects why we have not been able to commercially adopt these technologies. To list a few major ones: speed, accuracy, and robustness, or their lack of those qualities, have made it difficult for any automated or robotic machine to be used in practically used in these crops. For example, there has been a lot of efforts in robotic picking. I'll talk about that quite a bit in this presentation. We're still lacking some of these aspects to make it viable. Produce plant damage. For some of the technologies, particularly mass harvesting techniques such as sacking and capping fruit, we either damage plant or damage fruit and cause a lot of cause those damages outside of the acceptable range. And cost, lack of adoption. There is this cycle of starting with high cost of technology and that kind of limits farmers' ability to adopt them. And then limited adoption makes the economy of scale unfavorable for reduced cost production, and this cycle is difficult to break because of, again, the complexity of the machines, as well as sometimes a specialized need for these kinds of crops. And then also, to some extent, limited volume of these crops that are produced around the world. So WCC PASS program on agricultural robotics has been focusing on a few of these aspects, including crop harvesting, fruit crop harvesting to be specific. We have been working on addressing some of the challenges around speed, accuracy, and robustness through both mass and robotic harvesting technologies, different types of end effectors. When I say end effectors, that's the hand part of the robotic system, different catching mechanisms. When we're talking about mass harvesting or second catch harvesting mechanisms, we are investigating many different mechanisms to do that, and with different robotic system, meaning we are integrating sensing, manipulation, end effector, and many other associated components into various robotic systems to evaluate them in lab and field environment for apple and cherry harvesting particularly. Starting with automated cherry harvesting, we've been using a relatively big machine that has slanted capturing frames go from both sides of the trees, and shaker is actuated to go grab the branches or trunks and shake cherries gently and catch those fruit underneath. And we're also trying to aid a machine vision system, imaging system, and image processing system, to be specific, that would take or capture images both in daytime and nighttime. And the image processing system we have developed would automatically identify the trajectory of these branches, even when they are almost fully covered by leaves and fruit. We are still able to predict their trajectories, which then allows us to have an automated machine to go grab these branches and shake them. Robotic harvesting has been another big area for us. Over the past almost 7 years or so, we have been working in automated robotic apple picking. What we are seeing now in the video is the robotic manipulator and end effector system that, and machine vision system that that is used to identify and look at apples that have been developed. Those technologies have been developed under my program at Washington State University. And starting about 2 or 3 years ago, we started collaborating with a company out of Israel called FF Robotics. And through this collaboration, we have developed a full-scale machine. As we can see on our right, this machine has 12 arms. They operate in parallel, supported by our machine vision system. Repeating it here. And we have been testing this machine in Israel and Washington State, right close to where I'm located, and is showing a lot of promise for commercial adoption in recent future. A few issues we have been certainly still facing with this robotic system. One of those is robot canopy collision, meaning robotic hands are sometimes hitting branches and trellis wires. Sometimes there are fruit behind the trunk of the tree, and things like that. And there is also some issue with how we detach this fruit. Sometimes we are bringing a little branch with the fruit, and other times we are not picking this fruit with the stem on them. So we are trying to improve our image processing system to identify branches and trellis wires more accurately. And we're also trying to add what is called the orientation of these fruit into the vision system capabilities. And we will be using those into making decisions in terms of how this robotic hand would be used to approach this fruit and pick them. And we're also working on improving the way these mechanical hands are operated so that we potentially could improve the efficiency in detaching this fruit so that we don't pick as many branches with this fruit. As you can see in this slide, again, we have been adding this capability in the vision system to identify trunks and trellis wires more accurately, and also identify orientation of this fruit. I don't know if it is clear to you, but as you can see in these fruit that are colored, there is an arrow showing the orientation of the fruit, and that allows us to approach the fruit from a direction that would not interfere or that would not collide with the branches or other obstructions. I'll also talk a little bit about targeted second catch harvesting, which is a way of harvesting more than one fruit at a time. We also call it mass harvesting. A quick background in a few seconds. There has been a lot of efforts in shaking and catching fruit. For example, there are mechanical or mechanized solutions to harvest tart cherries and a lot of nut crops by shaking the trunk of the tree or the canopy of the tree with finger type shakers and catch the fruit underneath. But these kinds of technologies have been successfully adopted only for crops that would be destined for processing markets, such as making juice or jam, or for the crops that can handle mechanical impacts easily, such as nuts. Using those technologies for harvesting fresh market apples and even oranges and cherries have been still problematic because we are sometimes damaging as much as 60–70% of the fruit with those kinds of technologies. So in my research program over the last 4 years or so, I have been developing this concept of what we call targeted second catch. What it does is that it grabs a small section of a small branch of a given tree canopy and applies right amount of energy, which translate right amount of frequency, amplitude, and time of shaking these branches. And as you can see in this kind of a simplified diagram on our top right corner, the catchers can go right underneath where these fruit are in a multi-layer fashion, so that the fruit that were gently shaken off could be captured right underneath where they are, so that they don't have to fly several feet down onto the ground. This technique then can minimize the damage to this fruit substantially. As we can see in the next video, we have been using this kind of system over the last few years in Washington State using a research prototype, and we have been able to pick as many as 95–98% of the fruit in a tree for certain varieties, and we are keeping the fruit damage to less than 10% for a few important varieties. This is, I have to say that there is some varietal differences, but for some varieties, this technology is showing very good promise for commercial adoption. And we are really excited about it, and we're continuing this effort to further improve and potentially bring the damage rate a little bit down from 10% as well. Here is a quick video. If it plays, if it doesn't play, that's okay as well. Right now we are testing with 2 or 3 layers. However, we could increase it to 7 layers or 8 layers, as many layers as there are in this trees, so that those apples from the top would not have to fall that far. Anyway, let's switch the gear into a few other automated robotic technologies we're working on. One of those is around automated canopy and crop load management. We have been developing machine vision system, meaning again, imaging system and image processing system, including deep learning and other kinds of expert or machine learning systems, including expert system in understanding canopies, whether that be identifying where the flowers are or recreating the trees for identifying which branches needs to be pruned out. And then we're developing robotic solutions to go do something about it, depending upon what the operation is. For example, if it is robotic pruning, we have a machine system that we recently tested in the laboratory environment that has a capability to find where the branches are, identify which branch needs to be pruned out, and get there with a robotic cutter and cut those branches. As you can see in this video, it is slowed down for safety reason, but we can see the capability of this machine to identify branches, get to those branches in a right orientation, and cut those branches off. Again, every year in the winter, when these trees are in dormant season without any leaves on them, this process is repeated every year for all the trees in apples and cherries and some other crops. And we are going to test this machine in the field in the next couple of months. If it were not for the corona or COVID-19 pandemic, we would already have this tested in the field. Anyway, this is another area of our research and development that's continuing at Washington State University under my program. Another research efforts going on is on red raspberry cane bundling. I don't know if many of you know about this crop. This is a kind of a biennial crop. There are canes grown for 2 years. They fruit in the second year, and the second year canes are selected and pruned out. And then the first year canes are brought together and bundled into sturdy or firm canopies. And those canopies in the following year would flower and fruit. And again, this process is repeated. And to automate this operation, we have developed a machine that has a machine vision system to find out where these individual canes are, bring them together using a mechanical system, and then tie adhesive tape around them, again, to create sturdy canopies where these canes are not lying on the floor anymore, so that the fruit quality would be much better when they fruit next year. And then it allows for mechanical harvesting system to go through these canopies and harvest the berries. Here is a quick video on that. Continuing with other automation robotics projects, just as introduction, we are also working with wine grapes. We are developing both machine vision system and automated robotic systems to perform a few things in wine grapes. One of those is to identify cordons in this early growth stage in vineyards. As you can see in these images, as the shoots start to grow, the cordon, which is the horizontal structure, horizontal permanent structure of these wine grapes, becomes occluded, increasingly occluded. And as you get to fourth week here, pretty much entire cordon portions have been occluded by leaves and shoots. And our effort has been there to identify the structure and estimate the location of these horizontal permanent structures, which then allows us to develop an automated machine, which was also tested a few weeks ago. I didn't get time to include that in this presentation, but we have developed a prototype of an automated system that would follow the trajectory estimated here to perform a few things. One of those would be to remove some of these shoots, which is called green shoot thinning. This operation is important in wine grapes because if we leave all the shoots that are growing in a wine grape canopy, we would be fruiting more quantity than desired to produce quality wines. That's why farmers every year send manual crew to remove a portion of these shoots. And we are trying to develop this automated machines to do the same with the machine. And it could also be used for automated pruning, which happens during winter season, and a few other things that might happen in wine grape orchards, wine grape vineyards. This is just a comparison between the manual and automated identification of those cordons. We have been using unmanned aerial systems or drones to do a few different things, to perform a few different aspects of farming. One of those is chasing away birds. Bird is a big problem in wine grapes and blueberries and cherries and some varieties of apples. And we are developing this technology to automatically find where birds are and then send this drone to the direction of these birds and interfere or intercept their flights. Or if they're already on the ground, we would just go over where they are and make some noise and do some random flying so that these birds can be scared away. As you can see in these graphs, there is a substantial difference between when we fly these birds and when we fly these drones versus when we don't, in terms of how many birds are there in the field.
Dr. Manoj, sorry to interrupt you. There are a lot of questions people have. In India, they're starting stage, so they want a lot of information from you. I would recommend you that another 3 minutes, if we can conclude, so we can have question and answer. I think we need that help from you, please.
Great, thank you. So this is my last slide about the research, maybe one more slide, and then I'll spend a minute talking about a few future things, and then we'll be done.
Okay, thank you.
So another project we're working on is called Smart Irrigation. In the CERT, we are using many different kinds of sensors and Internet of Things to collect many different kinds of information, put them together into a big data analytic environment, and use this approach to make decisions when and where and how much water is necessary, and use an automated system to apply water in wine grapes to starting with. That could be useful in any irrigated crops. We're also using similar approaches for applying nitrogen at a desired level depending upon the needs of individual plants. As you can see in this particular picture, collected on the same day from the same orchard, They have different leaf color, which indicates that they have different level of needs for nitrogen. And based on these kinds of information, plus many other kinds of sensor data, we're making a decision in terms of how much nitrogen to apply in a given tree, and how to apply and when to apply. With that, let me spend just about a minute or two here on potential future direction briefly, and then we'll stop there. I'm just trying to introduce how many different pieces in the past have come together, from mechanization, automation, and robotics and precision management together into a concept what we call smart or intelligent farming, or sometimes we are also calling it agriculture 4.0. In this aspect, artificial intelligence and cyber-physical systems have been making a big impact for us to achieve what we call more or better with less with this smart farming approach. The techniques in artificial intelligence, such as deep learning and expert systems, have been used to perform a few specific things, such as pattern recognition and machine vision and big data analytics, and decision support system, robotics. All these disciplines are developed or supported by artificial intelligence and cyber physical system. What it means for agriculture is then that we are able to perceive plant conditions, make farming decisions, and implement those decisions very effectively, and apply that to water management, pest management, canopy management, and harvesting, and a few other things that has to happen in the field in an efficient way, so that we can apply right amount of input at right time and right location to create more of the agricultural products. And this, I think, will continue in the future, and will have achieved our goal of achieving smart farming or autonomous farming in many different kinds of crops. I will stop with that for the sake of time, and also I almost finished what I wanted to say anyway. Okay, thank you very much.
Thank you, Dr. Manoj. I think it was a very interesting topic for all of us to learn how the robots harvest, especially. There are some questions I have here. Before that, I'd like to remind the attendees as well as the panelists, you can raise your hand. Actually, if you don't know how to do it, you go right side bottom, there is raise hand symbol, so I can see, and then I can call each one for the questions. In between, I have got some few questions here to me come from other sources. I would ask the questions. There is somebody from Hyderabad, Lakshman. He has asked a question: how the harvester identifies ripened fruits or detaches only ripened fruits? Dr. Manoj.
So when it is robotic harvesting, it is not that difficult for the vision system to identify or estimate the color and size of the fruit, which are the primary visual indicators of ripeness. So this is relatively simple. However, quality is also dependent on internal parameters, and ripeness is also dependent on internal quality parameters such as sugar content and what is called Brix, which is basically the combination of sugar and acidity in this fruit, which is currently mostly done destructively, meaning farmers would go to the field and collect a few samples and kind of make a decision whether the plot is ready or a given block is ready for harvesting or not. But then also there are kind of proximal sensors using hyperspectral or multispectral signatures to detect internal quality parameters, which could also be included in these robotic picking systems, which we have not included so far. Let me spend another 30 seconds talking about the quality or ripeness for second catch harvesting, which is the most difficult challenge that we are facing actually. We are trying to apply right amount of frequency and amplitude in this secking mechanism. These are linear secking mechanisms. As you can see my hand, if I use different frequency and different amplitude, we have some indication that I might be able to harvest only the ripe fruit and then don't detach the unripe fruit. And if we repeat that process a few times over the harvesting season, we should be able to harvest ripe fruit selectively. But this is just the hypothesis. But then I have to add this. For a lot of commercial varieties in the state of Washington, generally fruit ripe together. For a lot of varieties, we pick them together anyway, even with manual harvesting. But for some varieties, we pick 2 times or 3 times. But for other varieties, we pick only once. In that kind of varieties, ripeness is not a big deal because we can identify this plot is ready and go harvest everything.
Thank you. Thank you, Dr. Manoj. There is some attendee, Mr. Sharagoda. Can you enable him speaking, please? Mr. Sharagoda, you can talk. You can ask your question now. You're hearing me?
Dr. Manoj.
Yeah.
Yes, sir.
Many people are interested, these young, researchers, that how should they start? Because this what you have done, you have shown, but how they should start the research? Where is the technology? How they should go ahead? So little bit time if you can spend, because many of this is just the technology as we have been asked that we should work on it, but how to go ahead? If you can with your experience, if you can tell us.
Sure. I think basic training certainly is important to work in any areas of research and development we would like to work on. For robotic or application of robotics and artificial intelligence into agriculture, I think some background education has been helpful particularly for me. If I talk about my example, my experience in computer science and machine learning and remote sensing technologies as I was doing my undergrad and master's degree has been instrumental in bringing those technologies, at least understanding how and what that means, and then creating this application environment in agriculture for those basics to come play its role has been instrumental for me. So there is some of that aspect, but it doesn't mean that any agricultural engineers with not much experience in machine learning, they are still able to apply these kinds of technologies into agriculture, particularly now because of some of the advanced machine learning techniques such as deep learning, with a lot of libraries available from Google and other companies that allows us to develop these kinds of solutions rather quickly, actually, with a limited understanding of the inside algorithms. But I think to be successful, creating a multidisciplinary team within your research environment, I think, is crucial. It has to have agricultural engineers like us. And if we can bring in expertise from computer science, who knows much better about machine learning and machine vision and expert systems and things like that. And then as important or even more important is to bring horticulturists or crop scientists who know about the plant, because if we develop our technology from just the engineering perspective, we might be just trying to solve a problem that is not there, or we might be just trying to solve a problem that's not practical. So I think creating this multidisciplinary environment where we can bring perspective from multiple different directions into these problems and creating a systems solution rather than just an engineering solution, I think is important. Certainly, writing successful grants has been another aspects of no matter what we do. I think that's true in India, certainly very true in the United States. These transdisciplinary teams have been also helpful in creating competitive and meaningful grant proposals that then could be successful in getting these federal or state grants to continue supporting our labs, both in terms of facilitating them, getting equipments, getting students, as well as then completing the research objectives.
Thank you, Dr. Manoj. I see Dr. C.R. Mehta has a question. Can you please, C.R. Mehta, this will take last question. Yeah.
Dr.
We
Manoj,
take
I
this as
have
last
one
question.
question. You have mentioned about two types of robots for harvesting of apple. One is like pick, pluck, and drop. Another one is targeted shake and catch. I think the second one, targeted shake and catch, will be having more output per unit time, and that may be having more potential for acceptance at commercial level. What is your opinion?
I totally agree with you. Actually, when I began that route, there were a lot of questions, and some questions were something like kind of a analogy to when we have Tesla now, why we are going to manual cars that were popular 80 years ago or 40 years ago. But I think even in the countries like US with relatively modern orchard architectures, robotic picking still is challenging for certain varieties. For example, red delicious apples, which are sold for like 70 cents a pound, using high tech for that kind of crop, commodity fruit with affordable cost might still be challenging. For crops like Honeycrisp and Cosmic Crisp, that was a newer variety created here, which are sold for like $4 a pound or $10 a kg. Robotics perhaps is better suited there. Anyway, my hypothesis has been that there are certain varieties, certain canopy architectures, certain geographic regions where one technology might be more appropriate than others. And that's why I'm trying to push both of these types of technologies as much as possible. Certainly managing funds to do research in a way competitive technologies is not easy, but my hypothesis is that these are not competitive technologies, these are complementary technologies, one being more suitable in certain situations than others.
Thank you, Dr. Manoj. I take
Thank
Dr. Dr. Gajal Singh has some question to ask.
Arki getting up early in the morning, making a presentation at 5:30. Thank you, Manoj.
Thank you. It's not a problem at all.
Thank you. I think we'll stop the questions now because next presenter is there. I think thank you, Dr. Manoj. Like Dr. Gajal Singh told, I think we can really appreciate, and we would love that you help more. We'll call you on specific topics. You help us to have the robotics starting in India with youngsters. Thank you, Dr. Manoj.
Thank you really very much for this opportunity. Really great to be here and to share what we're doing. I know some of you might have seen this, most of it, not everything certainly, but most of it in my presentation about a year and a half ago, maybe, in India. Some of you might be attending other seminars. Sometimes the content is similar. Hopefully you are not too bored, but for those who are new, hopefully it made some sense.
Thank you, Dr. Manoj. We have now we have the second speaker, and this is about for especially aimed at the engineers who are youngsters. What is problem solving with an example of case studies in agro processing engineering, and this will be presented by Dr. Narendra Shah, who is in IIT Bombay in Sitara, and right now he's visiting faculty in IIT Bangkok. Narendra Shah has completed his BTech in Maharashtra and Masters he has done in IIT and a PhD from France. In PhD he has done in process engineering, and he has been instrumental actually to establish Sitara in IITB because I know him from that moment, from that time. And he has been doing a lot of work on rural development, especially that's very important for us here. And I should add here, this particular webinar would not have happened without him. And another point I will add credit to him, this particular, my comeback in agricultural side in electronics, second time, which happened now is because of him. So this will keep it for some other time to talk. I think time is short. I would request Dr. Narendra Shah to come and say, please.
Yeah, am I audible?
Yes.
Can you all hear me?
Yeah.
Yeah. So good evening to the friends who are in India, and good morning to the friends who are in the other part of the world, in US. First and foremost, I would like to thank Dr. Indramani and Dr. Syed, and of course Professor Gajendra Singh for giving this platform to speak and share my thoughts on what skill sets the younger generation must have to do problem solving. And I will narrate this through some example case studies on the projects that my group has been conducting for last 4 or 5 years at IIT Bombay. Most of the recent projects I will touch base upon. And actually, to my young friends and more very young friends, it's some kind of a shifting of gear now from what the earlier speaker talked about, because the context is totally different. You know, in USA, for example, you have the smallest size of farm to be 200 hectares or 300 hectares. And very few people, as the speaker talked about, very few people to do this farming. Whereas in India, the conditions are exactly the other way around. You have large number of small farm holders, and you have still about 50 to 55, 60% people engaged in farming. So the context here is different. And as the earlier speaker spoke, I just want to catch one phrase. He said, more from less. Dr. Manoj, if you're still there, I would like to add one more phrase to it. I would like to say more from less for more. So if we can sort of do whatever a technology choice for, you know, more from less for more, it would be a sort of a great thing to do. I would sort of give this. Normally what happens is, like any lecture or any talk that one gives, it must be like a storytelling. And a story is very effectively told if you see your audience in front of you. So now it is really a challenging task. I don't see my young audience in front of me, neither in person nor virtually. So it is going to be a task. I will try to take you through my 20 slides and some video clips. And I hope Murphy doesn't come into play here. You know, I think all of you know what was Murphy's law. If something has to go wrong, it will. So let's can we move to the next slide, please? Yeah, so this was the introduction which Dr. Syed already gave. So I would like to go to my next slide. Yeah, so the first line what I have said is, engineers, like all of us here, need to solve problems. And if you do not solve problems, nobody will heed you, not the community, not your own peers, not your even family. So you have to solve problems. Now, in order to do the problem solving, I have put some 6-7 verbs here. What are the tasks of an engineer? What does the engineer do? So the engineer he observes in order to correctly define a solvable problem. When I say a solvable problem, for example, you can also put a problem definition saying that remove the poverty, or eliminate the poverty, or you can simply say double the farmer's income in next 5 years. So these are, for example, a large set of problems. Whereas if an engineer or a team of engineers is sort of given a problem definition, you need to observe, you need to see closely. Next is measure. So we have been hearing, for example, on the second day we had Dr. Syed and then Mr. Barure talk to us about what is the measurement, how do you do instrumentation, how do you parameterize your process, for example, and where, how much, and how do you estimate those parameters to solve the problem. Then, of course, once you have defined your problem, you have estimated, put the parameters, the sort of, independent variable and dependent variable and things like that. Then you design the process, or you design the equipment, then input and output. And as all engineers know, that you have on the numerator, you have output, and on the denominator, you have input. So what that defines is an efficiency. So when you design, you have to design for an efficient process. Then once you have designed, you have, have your concoction, then you construct or build your prototype. And once you have the prototype, you do pilot testing. And as we say, the first principle in engineering, the first time things don't work. So you'll have to iterate on your pilots. Then you get a pilot, for example, your process, which you sort of do a pilot testing and which is reasonably good, gives the confidence to the engineer or the engineering team that now the process is ready to be sort of, put it in the field, install it, operate it, maintain it. And once you have installed it, once the sort of machinery, once the equipment, once the process has been put it at the site, then you need to monitor the parameters like efficiency, performance, yields. So these are some of the verbs, for example, these are some of the tasks that lifelong you will have to do, you will have to conduct. Next slide, please. Next slide. Yeah. So particularly, for example, you will see this of late, these phrases like end-to-end problem solving, for example. And there's a lot of literature on this. What is end-to-end problem solving? How do you identify a problem? Like, for example, the earlier speaker, Dr. Manoj, clearly said that we are here to solve existing problems. Unless you give solutions to the problems that are existing, nobody is going to look at your technological solution or technological design or technological process that we have come up with. And then design thinking, for example. There's a lot of scholarly articles these days. You are in the right, next slide, please. You are in the right times, for example, that you have a lot of materials. Next slide, please. Next slide. So you are in the right time. At our times, for example, when we did our BTech and Masters and PhDs even, we didn't have so much of internet, and we didn't have the information right at our desk. You had to go to library, you had to do your literature review in some other forms. Okay, so in order to bring you to the context, for example, the context that COVID-19 has given to us, has put us to these kinds of difficulties. And when I was trying to do some kind of a SWOT, I think most of you would have learned or would have heard about what is SWOT analysis. So it's nothing but strength, weakness, opportunities, and threats. So these 4 things, I have put it in 4 different quadrants. And as you see in the upper 2 quadrants, you have 2 things which are opportunities and threats. And I would call these are externalities. So all the opportunities that come to you or all threats that come to you, these are your externalities. You don't have any control over them. Whereas what you have control on is all your internal things, which are your strengths and weaknesses. And on this, for example, when I talk about the skill sets, it's really the below 2 quadrants to face the situations which come through opportunities and threats. And what I really feel, and I would like to sort of appeal to the young engineers, that let us look at this COVID-19 and post-COVID-19, post-pandemic, that we have certain challenges which will be thrown open. You will be reading in the literature so many things that people think that the world order will change. There are already in India, for example, people are migrating back. There is a problem of casual workers. They don't know what to, they have huge questions and they are living day by day. They do not know what kind of livelihood, whether they can sort of will be absorbed by agriculture, for example. So this is a challenge really, or an opportunity really, for example, for the ag engineers. I mean, can we sort of look after, can we take care of the problems faced by these migrants who are sort of, who had moved, for example, for certain jobs and situations from rural areas to urban areas. So typically this was called by, Abdul Kalam, our ex-president, had called this as rural urbanization. Can we go to the next slide? And next slide, please. And the same thing, for example, in an article which appeared in last week in Indian Express by one of the known scientists of India, Dr. Anil Kakodkar. And he calls the same concept of rural urbanization as silage. So he combines, for example, city and village. And can we sort of bring the education and can we face this challenge? So let me just read this, for example. He said that the whole article is there, and I think my slides will be shared. You can read this article in Indian Express. And what he says, Dr. Kakodkar says that, you know, the education needs to be holistic. The research and technology and development and management of it must enable the the rural livelihood enhancement and technology enabled rural enhancement. And although the author says that it would take a while, for example, it is easy said than done, that it would be sort of quite a challenging task and a stupendous task to get the rural youth to become empowered enough to convert the challenges into opportunities in rural areas. So are we really ready as ag engineers, for example, to build our skill sets? Can we go to the next slide? So when I say about the skill sets, what are those skill sets? So I have categorized the skill set into two parts. One really are kind of soft skills, as you call it, and those are called analytical skills. And the second category is hands-on, or I would call it as a hard science or hard engineering. So in the soft science, what you have is like, you know, quantitative skills where you sort of use your, you know, knowledge in Excel and MATLAB and things like that. And whereas in the sort of hard science or hard engineering, you design, for example, you use the components, the electronics, electrical engineering, as what was talked about in the webinar of second day. So if you can take me to this link to give you an example of soft skills or analytical skills. So if, for example, the farmers ask you the questions like, based on the climate or based on the meteorology, what will be a likely sowing window for me? You know, because the Kharif season, for example, is coming. Month of May, people prepare their lands in many parts of India so that in the June, the onset of monsoon, the things are ready for sowing, for example, the Kharif crop. So what would be a likely sowing window? Should I sow a short season or a full season variety? Will there be a drought, and when? And will there be enough rain? Is there any forecasting? How will it spread? And when will I harvest? So these are some of the questions that our farming friends, our farmers ask. And for that, for example, what you need from your analytical skills is like you can sort of plot them that, you know, in most of the in India, for example, you have May, June, July, August, September is something when you get your rainy days, for example, or dry days between rains. And then what was the temperature? What was the radiation? And so all those, for example, your electronic stuff, for example, earlier people used, I think on the second day, Mr. Barure told you about the mercury in glass thermometer. But however, if we want to do, for example, the automatic recording through a meteor stations, you have to use things like thermocouples. You have to use things like sort of temperature measurements and humidity measurements and radiation measurements and do these kinds of plottings. Can we just run through the next two slides, and that will illustrate further the sort of okay, all right. I think I wanted to show the other two slides, but it doesn't matter. So this, for example, these two sets of skills, I have put it in a stem leaf model. So what is the stem and leaf model? So STEM means science, technology, engineering, mathematics, as we said, hard skills, and leaf means languages, environment, arts, and finance. Since all of you are from closer to agriculture field, you understand one cannot exist without the other. While the leaf does its photosynthesis and provides, for example, the stems cannot do the photosynthesis, but it provides the structural stability for the plant and for the leaf to be hold there. And what I have put, for example, the root is nothing but your family, friend, and social support system. So this is what I call it as in your skills, the stem, leaf, and root model. Next slide, please. So as we say problematics or the problem definition, what you're going to get through your sort of, employment, if you have, for example, or if you have, you are an entrepreneur yourself, and if you want to do a problem solving, what are the steps, for example? So you find out the need first, identification of a problem, analysis of a cause, analysis of possible solution, and action planning. And as we say, for example, what our social scientists tell us, that never ever do sort of, that arrogance of an engineer saying that I know everything, I have come with a problem, this is the problem that you are facing, and I have come with a solution and adopt this solution. There's a very less likelihood that, that your particular solution will be adopted and applied. So what they say that in your sort of approach, you should be always, it should be appreciative inquiry added to it, building the systems, innovating along with your stakeholder, along with the farmer, because he also knows few things. You need to sort of be cognizant of that and dialogue with him and develop a solution. What the social scientists call it as conduct, what you call as PRA techniques and focus group discussions and things like that. Next slide, please. So there is some from for your soft skills, you have, as I said, you are in the right time, or you are in the time when your literature review or study of the problems has become so easy. You get some data like this. We say, for example, 66% of the world's population to live in urban areas by 2050, and one of the index that we use is in 2014, for example, 54% already started living in urban areas. So which means it brings a challenge for the farmers. Next slide.
Dr. Narvesha, just 1 second. Sorry for the interruption. I'd like to tell all the attendees as well as who are watching, today 100% training session is there. Okay, it will start in another 5 minutes. So please wait. Those who are sending me all the messages. Training session today will be conducted. Sorry, Dr. Narvesha, please.
Session is very important.
Yeah.
Okay. So,
please, that is a connect.
Right. And so, for example, what I feel, what I reflected upon post-pandemic, what could be the challenges that agriculture engineering or agro-industry system would have? We may have some changing consumer demand, because already, for example, you would have people who would have come back and joined these forces in agriculture for the livelihoods and things like that, which perhaps cannot come back to the manufacturing sector or service sector. So when we say that the world order would change, these are some of the things that are the challenges which we need to sort of, as a fraternity of ag engineering, we need to look into. What are the advances of technological advantage, and what are the great dynamics that we have? Next slide, please. So one of the problems that we would be posed is like, how do we end hunger, achieve food security, and improve nutrition? Because if you look at the literature, you see that still 1/3 of the malnourished children below the age of 5 still are in India. For example, on one hand, we say that India is an arrived country. We are kind of trying to be a sort of, one of the major powers. But when you see a literature like this, that 1/3 of the total malnourished children live in India, it's really, we feel pretty sorry about it. And what skill sets, for example, we need to take to the agriculture, for example. So it needs to be more productive. We have heard about, more crop per drop and more from less and things like that. Okay, so how do you sort of make it efficient? Because the land size is not going to increase, whereas the eating mouths are increasing, for example. So how can we be sustainable? How can we be inclusive? So I'm very glad that, one of the last sessions planned in this webinar is something on democratization of technology. So what the democratization of technology will be sort of dealt with, I understand, is how do you make the technology inclusive? How do you make it transparent, and how do you make it resilient? And which is particularly, for example, in today's context of resilience, it is very, very important. And in this, for example, you need to sort of have a capacity development of young ag engineers like you, so that we can take this innovation system to accelerate the sustainable and green processes to enhance the impact. Next slide, please. So to illustrate my point, I'm just citing one sort of news item which appeared in Hindu of today, and you can look at the article leisurely when you get time. What that article says is like something like 2,500 tons of fruits procured directly from farmers are distributed to households. So you have heard about models like B2B, B2C. So this is really a B2C model. You know, the producer, for example, and you take, how do you do that? So often at times, of late, you have heard about things like FPOs, farmer producer companies or farmers clubs. And one which I can cite here is like, you know, a Sahyadri farmer producing organization, which is in fact, incidentally led by one of the ag engineer, Mr. Vilas Shinde. And I would like to appeal at this time to Dr. Indramani that like we had last year a meeting at ASPI of agricultural engineers. Perhaps next time we can hold a meeting there, because he has sort of demonstrated how, for example, the small farmers' income can be sort of enhanced by using this kind of technology integrations. Next slide, please.
Dr. Shah, you have, Dr. Shah, sorry, you have 3 minutes more.
Yeah, so what I will do now immediately is if you can pass on, so there are 4 case studies I wanted to talk about. If you can pass on the control to me, I would sort of show you the video of one of the technology, how we have done the value addition to jasmine flowers, for example, the small flowers, which are from a district of Palghar, which is nearby to Mumbai. What used to happen 10 years back, that all these mogra flowers or jasmine flowers were coming from through cargo flights from Bangalore to Mumbai, and there is this intervention of, you know, some today, I mean, like 10 years back, it started with 30 farmers. Now we have something like 6,000 farmers, and these are very, very small farmers who have 2 gumthas, 3 gumthas of, you know, very, very small farms, and they have 300, 600 plants, and they grow. And how, for example, their market chain can be improved by integrating a cold chain. I want to show this through video, if that is possible. If you can sort of.
Dr. Shah, Dr. Shah, you want a video or something? You have to take control. You have to do that.
Yes, if the control can
just
be
wait.
passed.
1 second, yeah. Please, can you give him the...
So control is all over to you.
Oh.
Only one video, please.
Oh.
Yeah, I will just show you one video.
Possible share screen to him, please. Setu, try share screen to him.
Shared, sir.
Will you share? Dr. Shah?
High value ornamental
Can you hear?
flowers
Can you
often
see?
seen adorning women's hair and used in celebrations across India. Of all the cultivators of mocha,
Can you please share the video? Share the screen.
highest in the state's production as outreach.
You have to share the screen. Okay, we have problem. Dr. Shah, you have to share the screen. We cannot share from here. Okay. Okay, let us.
Yeah, is it okay now?
No, it's okay. Let's leave it. No problem. It's not coming. Video is not coming. Doesn't matter. I think put back the slide. You want to have something? You conclude.
Kindly share that video with us. We will.
Yeah.
Okay. Okay. So let me come back to the slide now. Can I come back to the slides?
It's in your hand. Yes.
Yeah. So there are these 4 case studies. First one is like mocha flowers and how, for example, how we solved the problem which was thrown open by the small farmers. Then this is this cotton stalk, for example, which is burnt on the field because even animals don't eat it. It becomes hard like wood. So how, for example, we use the ozone technology to soften it and make an animal feed, animal nutrition out of it as a roughage, supplementation of roughage. And then also we worked on a process and product improvements in jaggery making from sugarcane. We have sort of, introduced some automation into this and improved the process as well as product definition, because jaggery is considered to be more nutrition friendly sweetening agent than white sugar. And also, for example, we have worked on some decentralized small scale seed storage units, because for large seed storage units, you have the air conditioning and dehumidification systems. However, if we can sort of, give them these sort of, farmers who could be our dealers, for example, of the seed companies who can store the seeds between the temperature of 14 to 18 degrees Celsius. So by using the Peltier effect, how you can low power consuming seed storage units So that was another case study. So all these videos and material is available. If anybody is interested, please send me a mail. I would sort of share this material with you. So with this, I would like to end my presentation here. And of course, there are two challenges for the next what is coming is one is climate change, impact on agriculture and food. And one more problem, as I said, the nutrition mission. Next slide, please. The nutrition mission, for example, last year, the government of India gave something like 9,000 crore, and ag engineers can definitely contribute. Like I have done 10 years back, I have designed the system and put it in Dharavi. I think most of you would have heard about Dharavi and the problems at Dharavi. Even in pandemic, there are huge problems in Dharavi. So I have put this unit right in the middle of Dharavi. There is a science hospital, and I have designed some what you call as RUTF, ready to use therapeutic food. How do you manufacturing it? How do you distribute it for the children below 5 years? Thank you, Dr. Syed, and thank you.
Thank you. People want to see your face at least. Can you close the presentation? People want to see live for a few seconds. There are some people told we want to see Dr. Nadir Shah, how he looks like. Can you somebody see? Yes, true. It came to me. So I sent them. He looks handsome, and he will come online after finishing. Okay, oh, it's true. And let's have something fun to laugh also. And it's true what it is. I think now you can see Nadir Shah. For those who want to see, he's really handsome still. And good. I think we come back. I think people are very keen. I'm getting a lot of messages. I'm really sorry that yesterday we stopped training, and we have to now go to the training because many people are, because it was advertised as training. So everybody's very keen on training. And today we lost about 10 minutes, 15 minutes, but we'll make it up next because we do have Saturday, Sunday, we have 3 hours. We'll make it up slightly. So I will now like to go for training session. I think first briefing to you what has happened till now in training. I will not show some slides right now. 2 minutes, I'll explain you what has happened, training what we had already in the first session. Then we will see what we are going to learn this session. So first session, what we learned, is my view is there on the screen or only another Shah view is there? Because people want to see, I can show my action in the hand. Obviously, it's okay. And now, first we learned about what is electron, what is electricity. Then we learned what is the current and what is the voltage, which means what is ampere when we compare it exactly with rate of flow, liters per minute. And we compare also pressure with voltage. And we come to the energy. What we've done is the watt or joules, what we call. Other side, this side is a watt, which is a multiplication of voltage and ampere. Then we came to the something little bit about how three-phase works. Three-phase has got 440 volts. That much we learned. We learned a little bit about, we have to worry about power factor. What is a power factor? That's a loss that happens in when you connect devices like motors and all. And that's an important factor. We have to go and read about it. Then we came to basic electronics. We studied about 3 of the basic components. A resistor, which is like a pipe, hydraulic pipe. Then we talked about an inductor, where the resistance varies. You can vary the resistance dynamically. That happens because of the change in frequency of the water flow in the pipe, or the change in frequency of the current flow in a inductor. Then we thought about capacitor, which can store temporary storage of electrons where you want to give it path. Then we learned about diode, which is like unidirectional valve. It will conduct in one direction. Then we talked about a diode, which is something like a Zener diode, which is about, like, let us say, a pressure relief valve. So it will not conduct unless the pressure is more. So that is a very important component which change the whole electronics, creating power supplies, everything you can do with the Zener diode. Then we come to the third one, a device that conducts in one direction. It will not, beginning it will not conduct, but if you give a trigger, let's say like a latch, pressure latched valve. So when I press when I give a trigger to that, it will start flowing, and the pressure of the water which is flowing, which will hold the latch also. So how to remove it? You have to remove the water completely. The same way they are called, those things are tracks which comes in both directions when they flow, where you control your AC motors, everything. Then slightly we talked about how to control with the, come to transistors. Transistors are valves, we studied. and which amplifies actually, and they are non-linear. So then we came to linear, which are operational amplifiers. So they are devices where you can amplify. These are like all amplify, opening the valves, opening the gates, sluice gate. This is the basic thing we learned. That was concluded actually as a basic electronics, what we need. That is a very large, huge subject. What I have given is just name of the parts, components which are used. It is the people who want to get trained on each one in the class, you must understand this particular topic. What I told you in short will be probably about 10 lectures in a college will be conducted. And I think we are all already BEs or MEs, so we can go and study which is required. So we will try again, attempt to go for the basic understanding of all the components used. So today we take up as digital electronics. What are the digital electronics? So we'll talk about what is it, like analog we saw already. Analog we saw, like I told you, diodes. And then we saw about transistors, which are operational amplifiers to say, and in between a transistor and a MOSFET, they're very close. That's all we learned. Now we come back to see digital, what is there. So that will take about probably 10-15 minutes. I would request my colleague, Mukund Iyer, to take up the digital electronics. Can you put the slides for him, please?
Thank you, Dr. Syed. I presume you all can hear me clearly.
Yes.
Thank you. Well, after the brief introduction given by Dr. Syed about the basic electronics, the analog systems, and things like that, today we move into digital electronics, isolation, signal isolation, that is, and signal conditioning circuits. Now, the first question that comes to anybody's mind, why should we learn digital electronics? Well, today whatever we use, let's say a laptop, a mobile, a tablet, or any computational object, they are all built on digital electronics alone. Now, whatever logic systems are developed, they are all from the digital electronics. We don't need an analog system to that extent for computational purposes, because we have the power of the laptop, the PC, to give us the solutions. So in order to have a better understanding of automation and other things, we should know digital electronics, as they are the building blocks. Now, in digital electronics, what are the different things we should know about so that we get a better understanding? Well, they are what we call it as logic gates, flip-flops, counters, decoders, isolation amplifiers, optoelectronic systems, and things like that. Well. It all appears to be just a jargon as far as a lot of people are concerned. So we will go into details of whatever details we can go into. Can we have the next slide, please? Yeah. So here we are. Digital circuits and logic symbols. Well, as you see, we've got about 6 symbols over here, which we call as logic gates. And what are they actually? Okay, if I say the first one, which is an AND gate, let's not get confused with the symbol or the truth table. Let us look at the AND gate as just a series circuit element. Now, what are the series circuit elements? Let's say we have a water line where the water is flowing, and we have an inlet and an outlet. And I connect 2 valves in series, one after the other. Now, it's very simple for me to get the output of water. I have to open both the valves. Opening any one of them is not going to work. Let me call the first valve as A and the second valve as B. So, what is a simple English language when we speak? We say A and B should be open. Yes. Now, this, when I say A and B, this is that AND. So, it's very clear. Now, when you see the truth table, a 0 value on A and B means it is off. or one value may get on. So in the first three conditions, when both are off or any one of them are on, there is no output. When both of them are on, there is an output. So basically, as I said, AND works out to be a series circuit logic. Coming to the next one, we have the OR gate. What we got? Well, OR gate. Now, what could that be? Well, it's very simple. We have the same water line, but now we have two parallel walls connected to one outlet. Now it's very clear that any one of them, A or B, I will have the output. Or I can start A and B also I can start. Both of them on, I get the output. Any one of them is on, I get the output. So this is basically the OR gate. Now comes the other gate, which is, we call it as XOR or exclusive OR. Well, to understand this, we had to have, just go back to our, staircase lighting systems, where we have two switches. When I want to go up the staircase, I just flip the switch at the bottom. I go on top, I flip the switch, which is there at the top level, and the light goes on. So one way the light comes on, the other way it goes on. So this staircase system, that is, if you see the truth table over here, when both are not there, A and B are off, output is off. When both A and B are on, again the output is on. Any one of them is on or off, then you have the output. So basically the whole building block in digital system is only AND, OR and NOR. Well, but we have 6 over here. Now what are the 6? If you really see, AND and NAND, they are just an output has been inverted. That is, I have just replaced it by a negation over there. Similarly for OR and NOR. And similarly for XOR and XNOR. So basically what we have is basic 3 gates, AND, OR and exclusive OR, which when the output is not it, we call it as inverted. We have the NAND, NOR and XOR. So that's how we come to the basic building blocks of the logic symbols and the logic gates. Now we'll go further. Can we have the next slide, please? So yeah, here we see some of the interesting symbols. They've all been jumbled up over here. Well, just to confuse you, for nothing else. Well, we learned about the NAND, NOR, and other things. So when we add them or we mix them in certain combinations, we get different circuits like flip-flop. What we have on top of the flip-flop, and then at the bottom we have a latch circuit. So now you see that the basic gates are becoming the building blocks of constructing a simple flip-flops and T-latch. Flip-flop, well, technically speaking, there are 2 inputs. I trigger one side, it comes on. I trigger the other side, it goes on. So we build systems with all the different types of gates. Now let's go to the next slide, please.
Wait a second. Just
yeah, sure.
Yeah, but
yeah, tell me.
Come back. Yeah, the flip-flop is something like first it is on. The next time when you say you press a button, it becomes off. Next time when you press, it becomes on. So it's a flip-flop based on its output will change based on the input comes. And latch is actually the lot of information is being talked. For example, now I tell to Dr. Indramani something, name I say, and tell something, Mukunda here say something. So they will capture, because I am talking, they will capture whenever the name is told. So they will latch the information, which is latches are very good for multiplexing. I have got 4 displays. I want display temperature here. I want display humidity here. I will connect all of them with the wires. I'll send one data, but one humidity will capture it, another temperature will have it. Please continue, Mukunda.
Yeah, so we'll go to the next slide. Can we have the next slide, please? Yeah. Now here, if you see digital circuit latch application, as Dr. Sab just pointed out about the latch function. Now here it is basically a latch, but this is a dedicated IC manufactured by a lot of guys all over the world, semiconductor manufacturers. This is what we call it as a serial to parallel decoder and latch. So it takes in the clock and the different outputs will be latched. So it basically multiple latches. There are about 8 D-type latches inside, but interconnected in such a manner that we can interconnect the ICs itself one after the other. So we can go on adding. Here we have shown only 2 stages of the IC. We can add a couple of them more and we can have n numbers of them. Okay. So this is one of the application wherein the digital logic blocks gates are used to make a dedicated chip to make it function the way we want. Okay. Now let's go to the next slide. Yeah. Here it's another set of ICs which are again dedicated. Here it is a serial to 7 segment. Now it's very interesting. You know, this 7 segment displays, whatever we see over here, we're very interesting. They indicate all the numbers, like for example, from 0 to 99 can be indicated. Now these particular semiconductors, whatever were there manufactured, they were specifically done in order to decode it for the 7th segment. But the building block again works out to be the same type of D latches and flip-flop, AND gate, NOR gate, and OR gate. So basically what, yeah, go ahead, sir.
Okay. The question is, you are talking about counters here. One of the application of digital circuits. You see, we saw in the last 2 slides, we saw OR gates, which are controlling actually functionality of different inputs and to get an output. Then we came to latch. Okay, latches, there are different types of latches are there to latch the information, which is coming to me, I will keep it till the next information comes. So my state is fixed. I keep it, that particular information with me. Suppose I say there are 10 valves are there, I say one valve to be on, the first valve will be on till next time I send the command on the same line. It's like a voice you are hearing, its own wire. Here we are talking about next level, we are coming here as a counters. There are some ICs available where you give a pulse, it goes on counting. You need not have a microcontroller for this. So this is a counter IC. Example here given with 2 of the 7 segment display, a counter. So another component you have in digital circuit is a counter. Next slide, please. So now you have another component here is multiplexer, left side. You can see it's multiplexer. Yeah, mouse, if you can move through, it will be very good. Host Setu, multiplexer written there. Okay, what is the use of this multiplexer? You have got, let us say, 10 temperature sensors. Okay, but temperature is very slow process in agriculture. You have got only one display. Okay, and or you want to send only one. So you'll scan first one, second one, afterwards, third one. So multiple can be, inputs can be given, and it will select only one output. This is one of the components, the multiplexing. You have the component, like even the speakers, when you have audio systems also, you have multiplexers. They're the same purpose it does it. For example, there are multiple people speak, all the microphones you put there, only one output, it will go there. That is a multiplexer. Then you have the opposite of the multiplexer, the demultiplexer. It's also another stuff where you have one input, it will go to different places, output. Depending on, you have to select anyway. The selection is done with 2 wires, whatever. This wire is on, the output will go there, this wire on. This is the block digital, how to switch. Next one, please. Now, so very important thing in digital circuit is what is interesting than analog and digital is the oscillator. They're precise. I remember Dr. Indramani says always the webinars or any program must be time. It must start on time, end in time. I remember that he is very timely in a point. That is what interesting in digital circuits. So he makes one pulse, something will happen. Second pulse, something happens. Third pulse goes on continuously doing. So you can really predict how it is going to work because you know so many pulses per second it makes. First second you will do this. First second you take a coffee powder. Second you put it inside. Third second you take and stir it, like that it goes. So very clear you can define. So oscillators are important integral part. We have different oscillator circuits and we use a crystal. For example, crystal is a resonant. Like I told you, it's very interesting. We studied this, how to generate electricity. A crystal is a resonant, which means when you vibrate them, they generate electricity in a funny way. So that is what the crystal we are using. Next slide, please. Now, this is isolation circuit and transformers. Isolation circuit is something is another important. The transformers are important thing we are talking, a component, a transformer. A transformer, we saw a little bit. There is two coils, center is a magnet. So one side is, let us say you got 220 volts, another side you got less windings to get 12 volts. So how to convert from 220 volts to 10 volts, you will have a transformer is the easier method to use it. Now you should know also from the, when somebody holds an appliance, whatever it is, how the isolation has to be there, otherwise the fellow will die. Here he will not die because the output what you see is a lower voltage. If it touches high voltage, no, here is no problem because isolated. Both are isolated. Next one, please. Now, isolation can be done one by transformer. You can isolate signals. These are very important in the field signals. See, you want to use agricultural sensors in the field. You have lightning problems. You have AC line lying around everywhere. See, whenever a glitch comes now, it will blow up the whole electronics control system for you. Yesterday, what you was talking, AP Ramachandran, it's very difficult in the field to work if you don't really isolate the signals out. So one of the isolation is the transformer. Not all the sensors can be attached. Second one is optocoupler. Optocoupler is whatever signal comes, whatever you want signal, the particular signal you pass through a light. And then from the light, you take it light barrier. So you transfer the whole information through light, not by wire. So only light will go. So there is no other magnetic interference will come. So normally problem is magnetism, electricity. Like, so this is through light goes. So that is called the optocoupler. Next one, please. Now, you also have a high frequency RF isolator. They are also available. These are actually, when you will come back to later on see the bus, the different buses, RF oscillators are cheaper and better and faster also, high bandwidth. So they also isolate signal. Input is isolated from outside. So you short something on the input side, nothing will happen to the output side. So your expensive equipment is saved. Only probably one sensor gets damaged. So that is the reason you have to know it's a building block of digital electronics. Next one. Now, next we see signal conditioning is another part of digital stuff. What is signal conditioning? We talked about analog and digital. Okay. Here I will explain a little bit. In microcontrollers, when you use whatever voltage is coming, let us say temperature 32 degrees. So temperature, we can measure many ways, like thermocouple is one of them. We'll learn that all afterwards. Don't worry if you don't understand right now. Two metals, if you join together, that's called thermocouple. They start conducting, depending on the temperature, they start conducting current. So you have temperature coming out as a current. Current means you put a resistor, it becomes a voltage. Okay. What we learned is only the basic blocks we'll use. So the current is flowing, I put a resistor, it becomes a voltage. I get a voltage. So when I get a voltage, how to connect it? I want a numbers format to transformer. That is called analog to digital. Now, analog digital is very important for especially agricultural applications. You have to be very careful because there are many factors out there. One is the bandwidth. That means how fast the frequencies analog signals can be converted. When you look for example, cameras or the RGB camera, they all have this, but very high speed you require. And then when you go for temperature or humidity, whatever you have sensors, they are very slow. So you don't take, for example, 10 samples in a second. You don't take thousands of samples. And sometimes you take tens of thousands of samples in types of camera and all those things come into picture. Now, there are how many types are there is very important. As agriculture, you must tell this is accurate, this is the type I want to have. Okay, this is very easy to understand. There are three types, I will say. Three types I have written there. Dual slope, successive approximation, sigma delta. This is very easy to understand. Let's not go into detail, but I'll explain the difference of it. A dual slope is normally can be used for temperature, everything, because normally you can get up to 10 conversion in 1 second. 5 conversion you want in a second. 10 conversion you want in a second. Most of the agricultural purpose, dual slope is enough to use it. Sigma delta is very, very accurate. Okay, very, very accurate. And when you want to go to sigma delta, we don't see much application we require in agricultural application, but certain few, there it takes long time. You want to have one sample, let's say 2 samples per second, something like that, you can use that. But there's coming back to the third one is successive approximation. This is very fast. It's actually approximate successfully, so it can go very fast. This is the one which are used in high speed when you want to convert from analog to digital. We come back to what is a sigma resolution. It's important now to come to all of them. What is the resolution? Suppose you have a temperature to measure. Okay, now I have a resolution of 8-bit. I call 8-bit, which means the maximum can be 256 steps. So if I 100 degrees is my temperature will give the whatever the voltage, I have used 8-bit. So maximum, if I want to see 256 steps only, I can have 100 degrees measurement. This is not enough sometimes, but outside temperature may be enough. But we have to be careful. Like when I saw in an example in Ludhiana, I saw temperatures they measure underground the soil and above the soil. When especially subsoil is very important factor. The soil moisture measurement device, unless it measures temperature correctly, it will give wrong reading of soil moisture. So you have to really measure accurate up to 0.1 degrees accuracy. Otherwise, you will not get soil moisture under the ground. You need that. So for example, one of the examples. So you need a resolution. 8-bit is less, very less. I think we need minimum 10-bit. 10-bit is 1000 steps, 1024, for example. 12-bit is 4096, 4000 steps. Don't worry now. We'll see all this binary and all we'll learn afterwards. So you have to choose whether you want to have 250 steps and you want 1000 steps or you want to have 4000 steps. So this is a resolution. Sigma delta very high accurate. I mean resolution is very high. 16-bit, 24-bit you get sigma delta. We don't require normally. It's a bit expensive also. But successive approximation, most of the purpose is enough for us. We don't require high speed, but the accuracy you get 12-bit. Most of the controllers today available 12-bit. At 4000 steps, you're getting all of them very, very nominal cheapest price. No need for you to go for 8-bit. Fine. Let's go to the next one, please. Now, this is the example of sigma delta, how it works. I think don't worry about it. I think this is a symbolic for those people interested. Go and be. I mean, principle very easy. There's a switch there which does. I think if you read it, you'll understand. I will design after this training program a question and answer separately for people who are really keen. And I think you have to write. I think we'll make one more questionnaire that we'll ask the questions then we plan for the people who are really keen to understand that we have to have separate. You see, this particular program, what we do, we have two objectives here. I told you two. Actually, I started to train only electronics to the agriculture engineers. But in between, I thought the agriculture engineers, some of them ask, why the hell I have to learn electronics? And some of the decision maker scientists say, why it's not my job, why I have to do? Okay, because we have to be careful because they never studied about it. So they cannot say, I don't know. When you are sitting as a professor post or something like that, you cannot, scientist, I cannot say, I know. So many times the problem, like today's speaker, he was an electronic guy, so he could do that. So what first aim is that for me. But second aim is to get the awareness for the people, what electronics is, why electronics is required. That is the reason these lectures are introduced to you. Because some people experts, yes, you have seen, you're in director position, you're assistant professor position, you have seen somewhere seminars, you attended all the seminars, agreed. But there are many people listening to this who have not seen this, which are B, agriculture engineers, they have not seen it. They see somewhere on YouTube, they don't understand. That's the video. We come back to the next slide, please. Now, this is a dual slope. Next slide, please. Now, this is digital to analog. We saw analog to digital. Same way from digital to analog. Why we need? For example, you want to change the speed of a motor. Speed of a motor. So they call 0 to 10 volts input. So that will vary the speed of it. So there are different motors are used in processing industry, which needs the speed to be varied. So they will have input of 0 to 10 volts. Mukund, you know about it, something about DA where it is used. Can you explain about some motors or some applications, please?
Yeah, well, most of the motor controllers today, even if you take it, consider the three-phase motors, whatever we use in the farm and other places, they all are connected via a VFD, what we call a variable frequency drive. Now, in a variable frequency drive,
sorry, variable frequency drive. Which means you can change the frequency to make the speed change. Okay, the motor output, the input frequency of the voltage. We learned 220 volts and 50 hertz is in India we are using. But this fellow is talking about giving 200 hertz, 1000 hertz, 5000 hertz, like that. He'll talk. Please continue.
Yeah. So what happens is in a three-phase motor, if you want to vary the speed of a three-phase motor, the only way you can do it is by changing the frequency. So that is why engineers develop the variable frequency drive, where you vary the frequency output, that is power frequency output to the motor. Now, in order to control the speed of that, what you have an option of giving it a DC voltage as the input. So 0 to 10 volt as the input. So as Dr. Sir just mentioned, Dr. Syed, that we have a to D converter. The system inside, that's a microcontroller within the system where it converts the 0 to 10 volt into analog voltage, by which it is converted back to D to A, that is digital to analog. And the analog voltage varies the frequency right from 0 hertz to 50 hertz. Okay, so this is where the D to A output voltage is being used. Yeah, carry on, sir.
Thank you. Next slide, please. Now we come to another part of signal conditioning. See, sometimes we get a voltage, we have to convert the frequency. And sometimes we have frequency, we have to convert to voltage. I give an example. In my own test, I will tell you. You want to measure some speed of a motor or something or somewhere a position. You have a voltage. See, voltage measurement is olden days was not accurate. For example, 8-bit resolution, which means I have voltage from 0 to 10 volts. I'll get only 256 steps. That's not accurate. But I change it to frequency, this voltage, because voltage and frequency, I can play with a capacitor and a resistor. Okay, so I can change the frequency. When I change the frequency, how fast the AC signal moves. Now I have the freedom. Frequency I can go very high level from 10 hertz to, let's say, 10,000 hertz. So I can measure this very fast in microcontroller. Microcontroller is very fast. They can count even 10 hertz. They can count even 10,000 hertz. So you will get so many steps. That is the reason V2F are used. These are all still used in many of the sensors, voltage to frequency. Whatever sensor you have, sometimes don't get worried about what is the voltage. Okay, voltage to frequency conversion required. We can use it. That's all your idea. Next one, please. Same, we will have frequency to voltage. For example, speed of the tractor, I measured slip control when I made. 2 of the wheels we had to measure. So I put an optical sensor which gives the pulses of the speed. Those days when I developed, I think I'm talking about 1978 in AIT. Okay, it's actually after it gives the pulses. It gives the pulses to me, and then that time no microcontroller was there in 78 when I started first. Then I tried to use analog. So slip is actually 2 speeds. I have to subtract and divide it from the actual theoretical speed. The actual speed I have to divide it. So how to get analog divider multiplier? Problem is I have frequency signal coming out from the tractor as rotation. How many RPM? How many pulses? Each rotation, for example, I don't know exactly now. I forgot. Maybe 64 or 128 pulses I was getting for each revolution of the tractor wheel, and it's converted to voltage. And I used operational amplifiers to multiply and divide. So you require sometimes the frequency to voltage also in agriculture application. That's all. These are all the blocks. This is not complicated electronics. I told you. Till now, what I taught you, is it complicated? Is it not possible? Agriculture engineer can understand. 100% you can understand. Now, detail, if you ask me why this resistor is put like this, why capacitor, yes, we will teach you also second level. But this first level, you know, it is easier for you, so you can go and read about it, because a lot of good material available in the net and books are available. We are lazy to read. We'll come back to the next important topic now. These 2 parts are the hurdle for anybody to think. It's like mathematics. When in schools, you don't like to study mathematics. You don't like calculus. So you don't like differential equations. Okay. This is something like this. It's analog electronics and this digital. These 2 are over. Then people are so happy. They will play with microcontrollers, which you'll see next one. Okay, but without this, you cannot go to microcontrollers. And that is one of the reasons. We will have a short introduction to microcontrollers today because time is short. We'll have a short introduction. So we'll know. We'll continue with that. Please, next presentation, please. Next presentation is there. We'll have, in the meantime, we'll have 5 minutes this presentation. Then we'll have a question for our next 5 minutes. So we'll close in correct time. And we'll discuss about how do we conduct. So microcontroller, I will go through fast probably to show you what we talk next tomorrow. So you'll have an idea. We are going to talk about microcontroller, what are the different components and what you have to worry about it. It's very simple. What is the flash memory? How much memory I should have for this application? I'll compare with applications and tell you. And what are the different features when I select a microcontroller to do? Because people come to me and say, Arduino I use this. I use this software. So people are I'm sorry for the audio disconnect. Now, so we will try to find out all the different components which are in microcontroller, how it is going to help us. Next slide, please. We will also talk about the microcontroller and the components which are used communication. These are not external communication much, only inside. That what is I to C, I square. Because why is required? I want real-time clock. I want to use it. Which type of chips you use? Then you have SPI, UART protocol. This is a different protocol. We'll talk a little bit about. Next one. I'll just show you what you're doing. Please, next slide. Now we'll talk about system on chip. Nowadays available, very popular. You got a very small chips. Next slide, please. Which has everything. What you talk, including Wi-Fi modules. For example, this I think people have reservation. Yesterday, one of the speakers was telling Wi-Fi didn't work when the height comes. This is the basic knowledge of electronics is a problem because the Wi-Fi is 2.4 gigahertz. It will the plant whatever the human body will have problem because your router in the house it doesn't work on the third room. You know it automatically if you have using a router in your house. So there are certain precautions we take it. For example, this one is used in Ludhiana up to 200 meters. Okay, the same in a farm. So it can be done. Next one. Now we'll come to next third one, which we'll talk also in as a single board computers. They are very cheap. They're starting from 700, 800 rupees. The down one, which is RPI 0, is 700, 800 rupees available in India. Okay, and the top one is more. You can attach a screen also. Everything. There's a Raspberry Pi, which is very popular with all the hobbyists and plus even professionals. And they are very good actually. You can use them in high-ended, but they cost around 3.5k rupees. Next slide, please. Okay, this is a different part. We'll explain tomorrow. Next one, please. Okay, we'll come back afterwards this tomorrow about different microcontrollers, accessories, what are connected. We'll talk. Okay, close the sharing, please. Yeah. Now I'll explain in short. What we have seen is only we saw today a digital electronic component. It's very easy latches. We started about flip-flop, then latches we came. Then we came counters we have multiplexes, we have demultiplexes. Then we come to understand about signal conditioning. That is from analog to digital conversion we have, and then digital to analog conversion we have. Then we have voltage to frequency conversion, frequency to voltage conversion. That's all. This is the block over now. Tomorrow we will talk about microcontrollers. We'll talk about how to select which microcontroller. Then what is pending topics? I tell you, there are a lot of pending. So the simple question is, what are the things can be connected to the microcontroller? Then we will talk about what are the sensors available, what are the features. This will take some time. Then after sensors, we will talk about what are the protocols used by sensors. Okay, like what type of wires are connected. A moisture sensor, soil moisture sensor. What type of SDA interface? What do you mean by that? So all those things we'll understand in these protocols. Then we come to the computation protocol. So this is the total what I think an agriculture engineer must know to go ahead. So now I think I leave to Indramani and some questions, suggestions. We have another 5 minutes because it's very important the panel to decide what knowledge level we have. People can ask questions now from the attendees, from anywhere questions regarding the training only. These questions, please. Anybody has question can raise hand or you can talk. Please, panelists, all you can open the mic, please. Any suggestions? Welcome. Dr. Indramani, any suggestions you get?
I think not on training. I think people are expecting, that we should concentrate on training. So from tomorrow onwards, more importance to training and interaction also. And I think, friends, you just send your suggestions. Are you understanding? Our Syed should go a little slow and I suggested him that go a little slow and put a little more time on the slide so that people can understand. But as we are telling that, as he explained that just have glimpses what he will be explaining so that you can have a little bit more understanding and come prepared for this training. So that is another purpose. No?
Yeah, Doctor.
Processing.
Uh, Syed, ICR has a course prescribed for agriculture engineers in instrumentation, electronics course. I think the team should look at carefully, and there are practical sessions defined in it. So we should review it, and if we can help them to improve it, and what kind of setup is needed and what kind of exercises they should do. Okay.
Yeah, I think I have seen some colleges where they course. I have seen some. I don't name the colleges. I've seen the lab also. They're basically electrical. They're basically electrical only is there. I don't think they have like AIT. We had instrumentation course in master's level, and I learned everything from AIT from Thomas's time. I still hold the knowledge to it. But I don't know. But ICR, I would like to know if I can help. Yes.
Yeah, Indramani has access to all those CR Mehta. I think they all have access to these, what are the curriculum and exercises. So if we can help the curriculum and the delivery of these courses.
After all
Dr.
webinar
Gandhi.
training series, we will go back to the course, and after discussion, we will try to upgrade those and bring these things into that course.
Okay.
Dr. Gandhi Murthy has a question.
Thank you so much, Dr. Ismail and Dr. Iyer for these sessions. So a few observations I had. When I started trying to incorporate these kind of electronics during my PhD and my master's, and later on, even as a young assistant professor who had basically no knowledge about this, the way I went about it was reading a lot of materials and things like that. But in recent years, I have been learning a lot of these things on the fly, basically by looking at a lot of the YouTube videos. There are some excellent YouTube videos. Basically, I wanted to just give a suggestion that perhaps we can compile a few of those videos that are already existing and give it as a homework for the viewers, basically our participants, to view that during the day and then come prepared for this so that they actually can see how to really solder. For example, these are practical skills that you can actually watch. And then how do you connect? For example, there was a lot of these opto-isolators, and I think in future you'll be talking about Arduinos and all the sensors. How do we connect sensors? There are some excellent videos that, for example, soil moisture sensor or temperature humidity sensor, these kind of things to automate greenhouses. There are a lot of home projects that people have done. And those are all really excellent things that we can give some onus on to the participants as well, because you are doing a tremendous job in trying to introduce something that is taught in like 3-4 years to people in like an hour session every day. And I think basically sending those videos will be good. Thank you.
Dr. Murthy, I really appreciate. The question is, I see still now the participants 52. When I started first, I thought only, I remember I told Dr. Indramani, I'm looking for 20, 30 only students to teach. That's what my first, but when I see the audience here, actually people say only training you do it. And then it's like classroom is that we can do that. But I'm looking at a much different level. I want in our scientist mind to go, yes, it is easy, this electronics. I will learn also. I will not only say some small fellow to learn, because really pitiable case, I see in some colleges I've seen, they're not a single person understand electronics. Like Dr. Murthy, there are few people who take interest and do it in every college, 1 or 2. Okay, but then that's not enough. Agriculture engineers only sanction. For example, drones. People are asking what I should do for drone. You should know what about, first of all, what is robotics. So you must know electronics. What is a BLDC motor? How to move? How to sense it? Like what are the color sensors? How do you differentiate? This all knowledge will bring in only because agriculture is a very fast field. I not blame them. We learn what all subjects we learn. Okay, we learn almost in the universe down the line, excepting medicine, human medicine. We learn everything. So I know it is tough. So this whole exercise to create awareness, and we will arrange again if those who are really want to learn step by step their problem, they can contact us directly. We'll make a method with Indramani discussing. We'll have some forum, and we can have a session in the daytimes or some other times also for those people who are keen. That's what my opinion. Dr. Indramani, please.
Thank you. No, it's all right. Thank you very much. I think things are going well, and now I will conclude. If you permit.
Yes, of course.
Thank you, friends. As promised, please remember that what we are trying to bring in, international experts, so that you should know where how to what extent these technologies are being used, how they are being applied. One, and second, some national, our own friends who are doing here in India, then this training program. So please, this is a kind of mix which can keep you, in a good mood. Otherwise, if 2 hours we talk electronics, then probably it will not be a very good, webinar. So I think this is okay, and we are every day we are getting some messages. Today's, take home, if I see, and that was in Manoj's lecture. He said, system solution, not engineering solution. Please remember,
Absolutely.
when I was in IIT Bangkok, Professor Singh was my teacher, and there was one class in which all engineering students used to sit in the last bench. That was agriculture course, and he said, "Come in the front, study agriculture." And that's how today Manoj said that if you want to develop system solution, you need agriculture engineer, you need computer engineer, you need horticulturist. So if you remain away from them, you cannot lead to solution. This is one very good take-home message. Please, and that's what we have been, and Professor Singh have been conveying in all meetings, in all lectures, that if you are, we have to develop solutions, so we have to don't forget, you are agricultural engineer. Without agriculture, you are not engineer. You cannot be problem solver. So this is very good, Manoj, from your lecture. And friends, tomorrow we'll have two very important lectures. One is on transfer function and mathematical models for electromechanical systems by Professor Soni from IIT Kharagpur, and he is also AIT friend.
Good.
And another will be from space-based sensors for mapping and monitoring, with special emphasis on agriculture, and SS Ray, who is national head, who is looking for this. He will be talking on this. So I have emphasized him that please talk about different sensors, starting from soil and going to space, how these things are being used. So he will be talking on this, and then we will have a wonderful session, a training session, and day by day we are learning and we are trying to improve it. Thank you very much, Professor Singh, and all my friends, and Syed and everybody. Thank you very much. We close here. Thank you.
Day 2 close, please.
Thank you again, everybody, for the opportunity. See you later.